relation, law of conservation of angular momentum. Am I right? Yes. Then we have to come to here today. The equilibrium of, yes. That is rotational equilibrium. Actually, what we have to discuss today. Thank you, Sharma. So again starts with physics. Okay, thank you. Yesterday ended with the Amolsa's class. Okay, then come to here. A rotational equilibrium condition. Ramesh Sir's class. Okay. Right. No problem. So today the concept is rotational equilibrium. Okay, in this rotational equilibrium, actually what we discuss. Equilibrium means net equals to 0. If it is a translatory equilibrium, in laws of motion chapter, we discussed net force is equals to 0. Okay. So right here, in case of translatory equilibrium, okay, by this I think you can understand it. Simply saying equilibrium is not correct. So which kind of equilibrium we have to say? In case of translatory equilibrium, we write F net on a body equals to 0. Means algebraic sum of all forces in vector form. Okay, algebraic sum of all forces, which is F net. This is translatory equilibrium. And when you come to here, this one I think Amos are taught to you. It is in case of thermal equilibrium. Thermal equilibrium, I think you know in thermodynamics chapter. They will acquire the same temperature. Okay. The body is in contact. Yes, in contact, have the same temperature. Same temperature. Okay. That implies T1 is equals to T2 equals to T3 equals to so on. What we say. How many number of bodies are in contact? All they have same temperature. This is final temperature. T final in equilibrium. And you are coming to here our class today. This is what is rotational equilibrium. Okay. In rotational equilibrium today, we say the torques acting on a body are equal. That is, net torque equals to 0. This is related to the torque, that is related to temperature, and it is related to the force. The three equilibrium here. In first year, what you learn. Okay, in rotational equilibrium, I say net torque, which is sigma tau, that equals to, I say, 0. Okay, it is a simple concept while explaining, but problem is we have to understand it properly, how to apply to the numericals. Okay, sometimes we won't find any information even. Okay, that we have to search in the numerical. Hidden information we have to search. How, sir? Give the problem, we try to identify. Okay, sure. If you are that much confident, I will give an example. Come to here. First, all the best. And then coming to the numerical. Here, he is saying that a spherical roller means spherical metal ball. Is placed against a step as shown. Where, sir? You can see it here. Suppose this is a roller, means a sphere, and it is placed against a step like this. These are the steps continuous. In that one step I am drawing here. This is a step. Height of step, here he gave it as some h. This is h, where h is the height of step. H is the height of each step. Okay, like staircase now. In the staircase, on one step, one roller is placed like this. This is a staircase. Understood? Okay. And then here, right, good. Then here, he wants to roll that step, that roller onto the next step here. This is the next step. He wants to roll it onto the next step. Means like this. To roll, we have to apply somewhere the force. Where he applied? He applied the force like this. Appear to pass through the center like this. Okay, where is the center, sir? Somewhere here. This is the center. Okay. And here he applied from outside like this. He applied the force. How much force, sir? Some F. Okay, a radius of the step is R. Take the radius as R. This is equals to R. Okay, then the question is, find the minimum force F, minimum force, to be applied just to roll onto the next step. This is the question number. How to solve it? I think if you see the question first, you can't identify. This is just a concept related to the concept of rotational equilibrium, what I strongly believe. Okay. Why? Because here, absolutely correct. Yes, correct. So here, net torque equals to 0 means at least 2 torques should be there. I am finding out one force. So how to find out the next torque and what is the other force? Try to understand. If possible, try to identify what will be the other force. See here, not getting any idea. Okay. Force by step. Okay, okay. Means normal reaction you are saying. Am I right? Normal. Okay, right. Look at the normal reaction, what the Amog is saying. Normal reaction is acting at the step star. When you try to roll, it leaves this surface and tries to come on to the other step by taking the support at this corner. So Amog is saying, sir, at the corner here, by the step, you will get some force like this, perpendicular to the corner. But problem, Mr. Amok, here, it is taking the support at this point, at that edge means you have to assume the axis of rotation here. Okay. This is the axis of rotation. Yes, correct. Axis of rotation. But problem is, normal reaction, look at, it is passing through the axis of rotation. One force passes through the axis of rotation, you won't find any perpendicular distance from axis of rotation. There is no perpendicular distance. Immediately I write here the torque due to normal reaction, tau, due to normal reaction equals to 0. First, all of you understood this step? Reason also I'm writing here, since it is passing through the axis. Right. Very good. It is passing through the axis. Yes, Sharma. Thank you. Okay. So there is no torque. So even though if you assume the force, there is no use. Amok. Yes. So we have to find out some other force. Got any idea? That one, what we neglect usually. Yes. Now you got the idea. Weight of the body. Yes. Not friction. Why? Because it leaves this surface now. Okay. So here the weight mg acts like this, vertically downwards. Okay. When you tries to roll it onto the other step, this force applies some torque like this, like in a clockwise direction. Then immediately this weight tries to roll it back if the force is not sufficient. Why? Because weight is left of this axis. Force is, look at there, the line of action of force at the top of the axis. At the top, you observe here. This is the line of action of force. So it tries to rotate in clockwise direction. Whereas mg, it is not sufficient, it tries to roll it back. So I am finding out two torques. One is clock, other is anti-clock. Understood this point, Nana, here? What I said, the torques due to the two forces. Yes, very good, very good. Then I say from the axis to the line of action, from the line of action of force to the axis, will you identify what is the perpendicular distance? How much is this? Will you identify the perpendicular distance from axis to the line of action? Wow, Amo, correct. R minus H. Okay, this is R minus H, correct. Why? Because total distance is R till here H. So remaining part will be R minus H. Okay, very good. So torque due to force I write here. Equals to applied force. Force into perpendicular distance. I write R minus H. Okay. Any doubt here, Nana, in writing the torque? Any doubt? No. Very good. So all of you understood how to find the torque due to force. Now you have to say wisely. What will be the torque due to weight? Torque due to weight, mg into perpendicular distance that we have to say. I don't think it is R, Nana, Ishan and Lakshmi Gayatri. That perpendicular distance is not R, what I believe. Look at from mg, line of action. Oh, no. Don't throw the options there. Here, look at. I think it will be the perpendicular distance from axis. Am I right? I think this is not R. Right. This is not R. You can say white line is R. Why? Because up to the center. So this one you can say R. And this red color part till here, you can say this part is exactly opposite to this side. Already you said this green color R minus H. So this is R minus H. So I think to find out this perpendicular distance, okay, you have to use some Pythagoras principle here. Correct? Okay. So using the Pythagoras principle, perpendicular distance, shall I write it as square root of hypotenuse square, that is R square, minus side square. Side, other side is R minus H whole square. So understood this step, Nana? Maybe. You are trying to solve it. Okay, good. R square, by expanding this term, R square get cancelled. What you said, 100% correct. I accept. That is, I think 2RH minus H square, Nana. After simplifying. Yes. 2RH minus H square. Now you can substitute there. Very good, Charnipriya. Good. Then here, torque due to weight, I write. Is equals to mg into perpendicular distance is root of 2RH minus H square. Okay. Then you can say here, sir, he is asking just to two rolls, sir. Means it is in equilibrium, sir. Just to two roll. It is in equilibrium. The two torques, one clock, other anti-clock, should be equal, sir. Means it is a concept related to rotational equilibrium. Net torque 0, sir. Diameter is not perpendicular distance. Oh, Manibabu. Diameter means who is diameter? From here to there, this is diameter. Nana. I'm asking from weight to the axis. This blue color I'm asking. What happened, Hangover, Is it hangover? Weekend hangover. Maybe. You are right, Amok. Okay. To the axis. What happened in the middle? Where you go? Okay, up to the axis of rotation. From mg to axis of rotation. Okay. Then here. Right, good. Babu Bangaram. Yes, right. Then here, in rotational equilibrium. In rotational equilibrium, I write torque due to weight is equals to torque due to force. The two torques must be equal. Net torque 0. So simple, I'm going to substitute here mg into root of 2rh minus h square is equals to here the other one, force into perpendicular distance. How much we wrote here? F into r minus h. So F into r minus h. That's it. Therefore, F is equals to, if they give the numerical value, substitute here. Mg into root of 2rh minus h square by r minus h. Okay, that's it. Over. So any doubt here in finding out the net force using the rotational equilibrium concept? No doubt. So I think you understood. Okay, good. Then look at, sometimes we feel, means those who are interested in physics, feel that the beautiness in physics. What is that beauty, sir? Hidden beauty. Okay, what kind, sir? You won't find any information in the question, but you will get the final answer in numerical. Really, yes, sir? Look at here. One question. This is a cubical block. Cube means all sides are equal. Keep in mind, that is not a square. It is a cubical block. Of side length small a, empty. Okay, it is placed on a rough surface, not smooth. Oh, sorry. Placed on a rough surface. This is rough. Okay, and here he is applying the force to push this block on the rough surface exactly at the top. Like this. He applied the force. Means like a tangentially at the top. Okay, that point I'm going to write. F is applied tangentially at the top. Okay. Then the block is in equilibrium. Okay. Keep in mind which kind of equilibrium not mentioned here. The block is in equilibrium. Find the coefficient of friction means mu. Mu equals to how much? Okay. I swear mu is a numerical value. Look at in the question, there is no numerical information. Okay. So first your idea. Do you have any plan to solve this question? Thank you, Sharma. On the block or in equilibrium, that you have to say. Lakshmi Gayatri. Plan. No plans. So we plan only on Sundays. Thinking, okay. Plans won't that work out. Anyway, we have to. Yes. Yes, Manibabu. What can you find there first? Uh, 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 F is mg by 2. How? How we get this F in terms of mg by 2? That too I got some doubt. You put the both the answers. Okay, right, no problem. Okay, in the meanwhile, we will try. He did not said it is in translatory equilibrium or rotational equilibrium. We have to think the problem. He applied the force tangentially like this means there is a chance to slide over the rough surface. There is a chance to slide the rough surface means if it tries to slide over the surface, rotational only. Okay, right. I don't think it's so. Anyway, I will try in my method. When it tries to slide over the surface, I think one force will oppose the motion. That is nothing but friction. Yes, correct. So I think friction will act like this. This is friction. Okay. But he said in equilibrium. In equilibrium means I think it is not sliding. Very good. This is correct only. Manikanta, to rotational equilibrium, what you are saying correct. Yeah, due to weight, what all of you saying is correct. But first, what I'm doing here, due to that force, is there any chance to slide or not? That's what I'm checking over here. So if it is about to slide there, then friction opposes. Since it is in equilibrium, I think he took the translatory equilibrium also. Yeah. So I'm taking from translatory equilibrium. Yeah, F is equals to mg by 2. Okay, right. That capital F, you are saying mg by 2. Not small f. In translatory equilibrium, yes, in translatory, from translatory equilibrium, I write F equals to F. One thing. Okay. And one more thing here I write, what, sir? Friction is zero. What you are saying, correct. First, we try to complete the translatory equilibrium. Another one is weight like this. Okay. And the next one is normal reaction like this by the surface. Okay. Look at there. It is mg and that is normal reaction. In translatory equilibrium, yes, we write it as here mg equals to n, another one. And all of you trying the rotational equilibrium. Yes, coming to your concept from rotational equilibrium. Yes, yes. Okay. Rotational equilibrium. When you apply the force, it tries to tilt like this by taking this corner as the axis. Yeah, that's only I'm writing now. Sharma. This is the axis. What all of you typed, that is correct only. Yeah. Many typed the same information, that is correct. Okay, this is the axis of rotation. From the axis of rotation, I think up to the force, all of you typed, that is correct. Perpendicular distance is A, that is L. From weight to the axis of rotation, perpendicular distance is exactly A by 2, that is L by 2. So this is here A by 2 according to my information, and it is A. Okay. And here the normal reaction is also there, but when it tries to tilt, the normal reaction won't act there, Nana. Why? Because this surface will lift up. When that surface lifts up, then the normal reaction will be shifted to there. Where, sir? Here. Why? Because this is the point of contact with the flow. So normal reaction will come to here. Okay. Look at there. Friction is passing through the axis of rotation. Normal reaction is also passing through the axis of rotation. So torque due to friction is zero. Torque due to normal reaction is zero. So we have to find out only the torques due to applied force and weight. So all of you followed this point, Nana? Whatever I wrote there. Okay. I am moving to the next phase. Yes. Not 1 by root 3. Manibabu. Yes. Not rotating. Just even it is about to tilt. Means rotational equilibrium. Okay. mg acts downwards only here, Nana. I put here mg downwards only. Right. So torque due to weight is equals to mg into perpendicular distance I mentioned in the diagram, that is A by 2. And torque due to force. Okay, no problem. The torque due to force into perpendicular distance is A. So tau due to F is F into A. Sahil Malik is there, Nana, in our class? Sahil Malik. Yes, okay, right. Then here, in rotational equilibrium, we write torque due to, yes, okay, Nana. Torque due to weight is equals to torque due to force. Okay. That is mg into A by 2 is equals to F into A. So F is equals to, you are getting mg by 2. Okay. Till here, most of the students got the information. Now you can use this information, what extra I gave here. That F you can replace with a small f. Okay. That implies since F is equals to F, frictional force, we can write F is equals to mg by 2. Again, since N is equals to mg, we can write F is equals to mu into N. Mg by 2. Where if you substitute N is equals to mg get cancelled. You will get mu is equals to 1 by 2. Okay. This what I said. I swear mu is a numerical value. But there is no numerical information in that question. Okay. This what I said. Those who like physics will enjoy such type of questions. Okay. Look at this one, previously given in exam only, not my creation. Yeah, true. Yes, previously given in exam only. Previous question. Okay. Any doubt in this question? Any doubt here in the first example or second example? Enjoyed, right? Thank you, Sharma. No doubt. Okay. Now we have to come to another subtopic, that is rotational kinetic energy. Means completing the, I already gave 2 examples there, how to solve equilibrium concept. So after completing the equilibrium concept, we are coming to rotational kinetic energy. If I ask the kinetic energy, usually all the students will try to say that is equals to half mv square. Why? Because till now we know this formula. Am I right? Usually we say half mv square only. But when you come to rotatory motion, problem is, yes, we have to replace v with rotational physical quantity omega. That's why what I write, when a body is in rotatory motion, yes, that only we are going to write now. I think one word, one term you missed it there, Charmi Priya. Just you wrote only half omega square. When a body, okay, we will check that. Is in rotatory motion, then actually we have to write for all point masses, we write, okay, the rotational kinetic energy as algebraic sum of all the things, that is half mv square. Till now what we know. Okay, means this is nothing but half m v I replace with r omega. Will you accept this thing, Nana? Will you accept? Yes, yes. That one simply I write like mr square into omega square. Of course, sigma is there. Okay. Yeah. Here you have to understand. For all particles in rotatory motion, omega will be same. Okay. Angular velocity, omega is same for all point masses. Yes, thank you. For all point masses. Okay. Then omega is taken out. What you are saying is 100% correct. Sigma half m r square. This one, even I think we can take half also out. Okay. So half omega square into sigma mr square, all of you know, moment of inertia. Therefore, the rotational kinetic energy I write here, half I omega square. This is the rotational kinetic energy. Okay. Translatory kinetic energy is half mv square. Rotational kinetic energy is half I omega square. Okay. Then try to interlink the rotational and translatory physical quantities, Nana. You will get some idea here how to interlink, sir. Once you check over there. Yes, you will get more idea. Sure. Charmakka, you are there. You are Unnava. Okay, come to here. Then here first I write the translatory physical quantities. And here I write rotational physical quantities. Yes, Manikanta, that's what I said. We gave, okay, we tried to put all the water from poles to equator now. Gave a chance to Sharat sir to take the class, but sir is not taking the class. It's very bad. Okay. Coming to here, the rotational and right, rotational and translatory physical quantities. No one is trying to do it. Who will do that, Nana? Bringing the water from poles to equator, is it easy? Not easy, just thinking. Okay, imagination. Yeah, coming to here, the physical quantities, try to interlate them. Here, first one, I write. Yes, yes, correct. So, displacement, comma, velocity, and acceleration. What we wrote there, all of you know, identical here. Who is identical to these physical quantities? Who are they? Shall I say angular displacement, angular velocity, and angular acceleration? Is it correct? Similar to translated physical quantities. Yes. Then, yeah, correct. Then second one. Here, the mass of a body. It is actually identical to whom? Analogous to whom? When you come to rotational. Anyone identify? Their mass measures inertia. Here, who measures inertia? Moment of inertia. Yes, moment of inertia measures the inertia in rotational motion. So mass is identical to I. Okay. And then who causes the motion? Simple. Force causes the motion. Translated motion. Then who causes here rotational motion? Yeah, exactly, Amok. That is nothing but torque. Yes, correct. That is torque. Yeah. Here, due to the motion, we will get a physical quantity that is linear momentum. Oh, sorry. Linear momentum. Yes. That is analogous to. Yeah, exactly. Angular momentum here. I think you are able to understand. The physical quantity is there and here. L. Okay. And here I write F is equals to dp by dt, rate of change of linear momentum. Here also we got one equation. Tau is equals to dl by dt, same thing. Yes, yes. This is another one. Okay, relating those two. Yes. And here we got F is equals to ma. Same equation, type of equation we got there. Tau is equals to mass is analogous to I. Yes. Acceleration A is analogous to I alpha. Tau is equals to I alpha. Now able to follow, Nana? And here linear momentum. Yes, P equals to mv we wrote. Yes. Same thing here we write. L equals to mass analogous to I. V velocity is analogous to omega, I omega. Same thing only we derived in the class. Okay. And next, according to law of conservation of linear momentum. Okay. F is equals to 0. Then L equals to constant. Sorry. P equals to constant. That implies mv is equals to constant. Same thing what we write here. When you come to there, when torque equals to 0, 100%. Okay. When tau is equals to 0, that is if tau equals to 0, then instead of P, I write L is equals to constant, law of conservation of angular momentum. That implies, here I write, wait. That implies, you can write I omega is equals to constant, law of conservation of angular momentum. Okay, right. And here extra you can write these things you learned in the class. Okay, extra thing what's look at that. Okay, this one also you learned kinetic energy. Ke is equals to, you learned one more, that is half mv square. Same rotational kinetic energy, here we learned it as half I omega square. Ke is equals to half I omega square. Okay, extra things. What's just 1 minute, Nana? Give a chance. 1 minute only. What a chance here. Okay. W is equals to, right. Thank you. W is equals to, you know the work energy theorem, na? Half mv square minus half mu square. Right. And W is equals to integral F dot ds. You know to formulate there, na, for work done. Same, try to write the same equations here. W is equals to half mv square. I write half I omega square minus half. Right. Mu square. I write it as I u initial angular velocity omega naught. I will take. That is power, I think. Here. Very good. Manibab. W is equals to integral. Force is tau, torque is analogous to torque, and into displacement is angular displacement, tau d theta. Exactly, you are right. And you can write the power also. There what we learned. Power P is equals to work divided by time. Of course, that is equals to integral F dot dV. Remember, Nana, F into V. Yes, same thing you can write here. Okay, this is power. is equals to, we write, same work divided by time, that is equal to integral tau dot velocity, I write it as d omega. Look at those things, no need to discuss that, what I'm saying. No need to discuss this formulae. You have to develop the new formulae in rotatory motion. Now you understood the relation between translatory and rotational physical quantities? Yes, yes, yes. Okay, now I can stop the class, Nana. Okay, if you want the pages, you can take. Oh, today we got 4 pages.